No nation which expects to be the leader of other nations can expect to stay behind in this race for space.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and thank you for your support on Patreon. We appreciate you. China has big plans to build a colony on the moon, and they clearly have the technology in the 2020s to accomplish what the United States did in the 1960s. The question is, will they do it before anyone else? The United States of America plans to return to the moon, this time to stay.
Is to return to the moon by 2020 as the launching point for missions beyond. Beginning no later than 2008, we will send a series of robotic missions to the lunar surface to research and prepare for future human exploration. Using the Crew Exploration Vehicle, we will undertake extended human missions to the moon as early as 2015, with the goal of living and working there for increasingly extended periods of time.
Now, as you saw, we've said this before. 30 years ago, in fact, with the Constellation program. But that was canceled. More recently, NASA had been betting on the SLS, Space Launch System, but recently admitted that the expense is not sustainable, something we've been saying for a long time. America's hope today is on SpaceX and the Lunar Starship, and if all goes well, sometime next month, Starship will launch again. But SpaceX will need to use a complicated orbital refueling maneuver to make it to the moon. Today we are going to explore another option, a faster option. To know why, we'll briefly go back to the start of the space age. Theoretical rocket science started with the great teacher Tsiolkovsky in the Russian Empire and later the former Soviet Union, and Robert Goddard in the United States. Both were ignored and often ridiculed by their respective nations. Soon there were others writing about humanity's potential future in space, including the Frenchman Esnault Potelier, probably I butchered that, and two Germans, Hermann Oberth and Fritz von Opel. While the others had been theoretical rocket scientists, the latter two were experimentalists, as was Robert Goddard. Not happy with just writing about the possibility of rockets, they started building them. Now understand that I'm not talking about solid fuel rockets. The Chinese clearly had developed these centuries before. I'm talking about liquid-fueled rockets, which are much more efficient than solid rocket motors. When we look at solid rocket launch systems, like those still used by India and in the Minotaur rocket described in depth in this lesson, we see they overcome this inefficiency by adding stages. Staging of chemical rockets to reach orbital velocities is necessary for even the most efficient chemical system on Earth, if you hope to get much mass to orbit. The pioneers of peaceful rocket science never got adequate funding, and the first successful liquid-fueled rocket was sadly an instrument of war. A single-stage chemical rocket system can work fine for ballistic Earth-to-Earth trajectories. The U.S. military is looking at Starship for this purpose. But single-stage to orbit systems, though popular to think about, are just not practical on Earth, without either an air-breathing first stage or a massive rocket with a tiny payload. Chemical rocket staging makes spaceflight from Earth possible. Staging works by getting the next stage to a new altitude and velocity, reducing how much work it needs to do. One of the considerations of rocket staging is the volume and mass of the different stages. It is beneficial to have a lot of thrust in the first stage. For this reason, many rocket systems still use one of the first rocket fuels developed, kerosene, a refined form of which is called RP-1 for the US or RG-1 for the Soviets and now Russians. It is an excellent fuel because despite not being as efficient as other fuels like hydrogen, RP-1 has a much better energy density, which means that the tank doesn't have to be too big. The giant tank on the space shuttle was, of course, for hydrogen, with a little bit of oxygen in the nose. The density of liquid oxygen is about 1,250 kilograms per cubic meter, and for kerosene it's about 1,000 kilograms per cubic meter, more if it is supercooled, while that of hydrogen is only 71 kilograms per cubic meter. And this brings up turbopump sizes. All of these engines are using liquid oxygen, and you can see their relative sizes and power output. If we turn specific impulse into exhaust velocity for these engines, then look at the thrust of the engines and turn that into kilograms per second, mass propellant flow, keeping in mind that the oxygen to fuel ratio is different for each engine, we can see that the pump must move a lot more volume of hydrogen than it does methane, and the methane engine must move more volume than the RP-1. That means that for the more efficient fuels you need a much bigger pump or a much faster pump, both of which put a lot of strain on the turbine blades. Using a denser fuel allows for smaller tanks and smaller turbopumps, simplifying the first stage. The first stage is all about power. Thrust exerted over a distance per unit time. The most powerful rocket to ever get to orbit is now the SLS, producing 8.8 million pounds of thrust, 15% more than the Saturn V. The Saturn V, however, could get more mass to orbit. That is because, in my opinion, the Saturn V had a much better design. Let's compare these. The first stage of the Saturn V is massive. At 10 meters in diameter, it is wider than the Starship or the core of the SLS. RP-1 fueled, burning with liquid oxygen, it has 5 F1 engines, producing 34.5 meganewtons. The SLS has 4 reflown Space Shuttle main engines, and these 2 solid rocket boosters, producing a total of 39 meganewtons. The second stage of the Saturn V is a hydrogen-fueled rocket with J2 engines. By itself, it is a massive rocket section, about 25 meters tall and 10 meters wide, with a mass of 480 metric tons, 443 of which is propellant. The second stage produces a thrust of 4.4 meganewtons. The SLS is more complicated, with the core stage continuing to fire after the boosters separate. Once all of that fuel is gone, the interim cryogenic propulsion stage, with its super-efficient RL-10 engines, is released, and goes on to the moon. The SLS can get up to 27 metric tons to the moon in its current configuration. Other variants were planned, but its cost of over $27 billion to date makes that unlikely. The Saturn V third stage is called the S-4B, also using hydrogen with 1 J2 engine. This system took the first humans to the moon. And while I love the technology in the SLS, especially the amazing Space Shuttle engines, these are incredibly expensive, as is the rest of the rocket, and they get thrown away every time. The SLS is simply not a viable long-term solution to human colonization of the moon. But if Starship flies, even if it is expendable, it will not obviate every other rocket system on Earth, unless it can be fully reusable. The Starship itself will just be able to reach orbit and return. It can release satellites, but to go anywhere else, it will need to refuel in orbit, something that has never been done at this scale before. When it comes to colonizing the moon, could we do it with Starship in a single launch? Let's see if this can be a viable solution. First, we will turn Starship into a regular, expendable rocket system, with a methane-fueled first and second stage, and we will add a third stage, by giving this part its own engines. We'll look at using methane fuel first. Elon has said that an expendable Starship using version 3 Raptors can get 250 metric tons to orbit. Let's see if that pans out. If we take a specific impulse of 330 seconds for the Raptor engines at sea level, and 380 seconds for the Raptor engines in vacuum, and calculate our ejection velocities, then take the reported mass of the booster and its propellant, then take a dry mass of maybe 100 metric tons for the second stage, down from 120 since we don't need to worry about these giant flaps, and its propellant, and add 250 metric tons for the third stage and payload. What does that give us? Starting with a total mass of 5,130 metric tons and burning all of the booster propellant, we end up with a final mass of 1,730 metric tons. Using the rocket equation, we multiply exhaust velocity at sea level times the natural log of the initial mass over the final mass and get 2,187 meters per second. And then separate from the booster and fire the second stage. That starts us with 1,550 metric tons moving at about 2.2 kilometers per second. We burn all of the second stage propellant and burn out with a mass of 350 metric tons. This is the added mass of the empty second stage and the third stage. Using the rocket equation again, we get 5,547 meters per second. Adding these up gives us 7,735 meters per second. And that's not enough for orbital velocity, which is a minimum of 9,400 meters per second. To go from low Earth orbit to the Moon would require about 4,000 meters per second more. If our third stage of 250 metric tons fires up for the Moon, how much propellant will we burn to get there? We take our rocket equation and we rework it. dV equals VE times the natural log of initial mass over final mass. Therefore, dV over VE equals the natural log of initial mass over final mass. E to the power of dV over VE equals MI over MF, and MF equals MI over E to the power of dV over VE. We were short about 1,665 meters per second of delta V from reaching orbit. Then we need about 4,000 meters per second to get onto the Moon. That gives us a total delta V need of 5,665 meters per second. If we plug these numbers into our equation, remembering that E equals 2.7183, we get a final mass when we get to the Moon of almost 55 metric tons. The Apollo 11 system was actually more of a four-stage rocket, with an RP-1 first stage, a hydrogen-fueled second and third stages, and a hypergolic fourth stage, which is actually the AJ-10 powered command and service module. Altogether at launch, the CSM and lunar module had a total mass of 43.9 metric tons. So if we want to land on the Moon with Apollo hardware, we should be able to do it with a single expendable Starship. But we don't have Apollo hardware. The only capsule capable of returning humans from the Moon right now is Orion, with a mass of 26.5 metric tons. And the only lunar lander besides Starship is the national team's, at 36 metric tons reusable. These add up to 62.5 metric tons. 62.5 metric tons is too heavy. But if we use hydrogen instead of methane on our third stage, with RL-10 engines, we can get at least 450 seconds of specific impulse. And rerunning the numbers, now we can get 69 metric tons to the Moon. That leaves a safety margin of 7 metric tons. No problem at all. And no need for refueling in orbit. I would argue that all we need to do is use what is available today, with the understanding that the national team lander is still being built. These lessons are not to argue that we have worked out the way to accomplish a mission. Orbital refueling will be necessary to bring enough cargo to Mars with chemical or even nuclear thermal rockets. These exercises are designed to make you consider alternatives so that we can have a better understanding of space science. Something to think about. Let us know what you think. Thanks for listening, and stay safe. Ad Astra Pro Terra.
Going back to the moon sustainably means an enormous amount for science. We barely scratched the surface with Apollo. Discoveries are going to happen. I can't tell you what they're going to be. If I knew, they wouldn't be discoveries. Okay, but it's going to happen.
The national team is the kind of outstanding leadership, outstanding experience that I like to work with. Blue Origin itself brings innovation and modern thinking to the table. Lockheed Martin and Northrop Grumman and Draper all bring an extraordinary experience, not only from Apollo, but before Apollo into the present.
The combination of our heritage aerospace experience has created a team that I think really uniquely is able to meet the target that we have set for ourselves.
The HLS is a three-element architecture, our design. It consists of a crewed vehicle, an ascent element. This has the life support systems for the crew, all the displays, the controls, everything that the crew will do to interact and to land on the surface of the moon.
We're taking the Orion heritage and we're bringing that into the ascent element for the HLS program.
Familiarity with displays and controls plays a very important role in safe human spaceflight. The first thing is that it minimizes the amount of training you need to do. And the second thing is it makes operation of that system that much safer. They're using the same displays and controls technology that they used on Orion, and astronauts will be very familiar with that.
The next element in the architecture is the descent element. This is the landing element. This is what will actually have the thrusters, the legs, the systems that are going to be able to land those astronauts and give them that safe, comfortable touchdown on the surface of the moon. And so this is being built by Blue Origin and is based off of our Blue Moon lunar architecture.
You know, we've flown our New Shepard launch vehicle many times. It uses a pump-fed hydrogen engine that can throttle down to 20% power level. And the reason that we do that on New Shepard is the same reason that we're doing it on HLS. It's for the lander application. And the BE-7 has that same capability.
And then the final element in the three-element architecture is a transfer element built by Northrop Grumman.
Specifically, the transfer element avionics, its computers, its software, its sensor suites are derived directly from the Cygnus service module. It's particularly relevant as NASA uses that platform to routinely deliver cargo to the International Space Station, and it's the primary heritage source for the transfer element.
And so this transfer element is the element that takes the ascent element and the descent element from a deep space staging orbit down to an orbit around the moon where the descent element can then land the ascent element on the surface of the moon.
And of course, us at Draper, we've been working in guidance, navigation, control, and avionics solutions.
We've been developing the BE-7 for several years. Cygnus has been flying resupply missions to the space station. Orion has been in development for a long time. And so these technology demonstrations that have been developed in the context of those programs have already been underway.
So we're bringing a proven heritage and we're bringing it together as a national team, and that is the value and the real strength of this three-element team.
It's amazing to think that we're only 6 months into this program, and the number of tests we've done on this program compared to anything I've ever worked on before is just mind-boggling.
In the base period, we've conducted a campaign of 25 specific risk reduction tests in 8 technology areas that are fundamental to returning humans to the surface of the moon.
The BE-7 testing is happening out at the East Test Area at Marshall, a place I know very well, and is excited to see when companies bring their work there, because Huntsville and Marshall in particular has a lot of capability in helping teams be successful.
We've run docking tests between our elements.
The rendezvous and proximity operations test went really well, where we're using actual LiDAR sensors to test out docking with already existing software.
We have another very critical set of demonstrations associated with our cryopropulsion module. In fact, we've just completed a thermal shock test using liquid nitrogen in a subscale version of one of the tanks that we will be flying on the transfer element.
We've taken our sensors and flown them on the New Shepard vehicle right to the edge of space, being able to test those sensors as they execute a profile that's going to match the speeds and the altitudes that our actual sensors will see as they go down to the moon. We have a full-scale model of our vehicle down at the Johnson Space Center, where the crew is able to come and interact with that vehicle, test it out, kick the tires. So one of these key tests that we just completed was an ascent from the lunar surface. And we used over 1 million lines of flight source code.
One of the most important things about the way we've chosen to do this is that we have a demonstration flight of our descent element 1 year before we actually send humans down to the surface. And that provides an enormous amount of risk reduction. We get to practice. We get to try everything out first without crew on board. And so we learn from that. We're going to learn an enormous amount.
So you could use it not only to take this stack down to low lunar orbit, but other things if you had another type of payload.
The division that we have between the elements also allows us to upgrade in modules. So not only will we get that first mission to the moon as soon as possible, but we will then be able to follow an upgrade path to continue to get to the moon in a sustainable manner. Our liquid oxygen, liquid hydrogen based architecture for our engines, for our reaction control system, and even how we generate power on the surface of the moon are resources that can be utilized and mined directly from the moon. That will form the basis to then fly cargo that will allow humanity a permanent presence on the moon.
Okay, when you land on an unprepared surface on the moon, no landing pad, there are bad things that can happen. First of all, the engine plume can accelerate particles on the surface. I'm talking things like gravel, okay, shrapnel at velocities of kilometers per second. That's dangerous stuff. The other thing that can happen is you can crunch your engine on the ground when you land. That happened on Apollo 15. Good thing is, in our design, with a separate descent element and then the precious stuff, the crew and the ascent engine on top, you're out of harm's way. It's safer. It's so much safer.
Our lander is designed to handle a fair degree of slope in the lunar surface it lands on, up to about 12 degrees.
The crew cabin is about 30 feet off of the surface of the moon. The radiator, the antenna, the solar arrays, those are lifted off of the surface. The astronauts can see out the window, they can see the horizon and use that for some navigation. The national team's human landing system allows us to abort at any phase of the mission and at any time during a 6.5-day stay. Our solar arrays are fixed to our vehicle. We have engine out capability.
One advantage of having the hatch on the ascent element so far from the lunar surface is that it will help mitigate the dust issue. The dust is very sharp and it clings to things. It's also not good for the lungs. So any time you have for that dust to fall off is very helpful.
Personally, I'm most excited about the mission to land the first woman on the moon. I think that's going to inspire the next generation of students.
Having been part of the leadership at NASA for a long time, particularly during lean years, it was really exciting for me to hear that the national team has teamed with NASA and has hundreds of millions of dollars of task orders planned at all the NASA centers, including Marshall, utilizing the expertise that the agency has and the unique facilities that NASA has to bring.
It's a remarkable team, and certainly is one which the United States, as well as the participants, can be very proud.
When the crew of Apollo 17 left the moon and Eugene Cernan climbed up the ladder for the last time, his quote was, "We leave as we came, and hopefully as we shall return, in peace and with hope for all mankind." And I think the shall return is a part of there that's really motivated me ever since the beginning of my career in space exploration.
We have to use the resources of space. We must have a future for our grandchildren and their grandchildren. We were given a gift, this nearby body called the moon. And it's this generation's job to build that road to space so that the future generations can unleash their creativity. None of this is easy, all of it is hard. Big things start small.